And this will also be helpful for your test, right? So better that we do the revision very nicely. Yes or no?
Yes.
Right? Good. Electrostatic force, very nice, right? So are you all clear with P and junction?
Yes.
So can anyone tell me what is P and junction? So some of the terminologies I'm writing over here, let us discuss. All the terminologies sounds familiar to all of you, right? Now at least you will be knowing something about it, right? That what is P-type semiconductor, what is N-type semiconductor, and when we bring this P and N-type semiconductor together, we get a PN junction, right? So it was something like this. So when we consider a P-type semiconductor, that please. Yeah. Okay, thank you. So in the N-type semiconductor, can you tell me that which are the majority charge carriers and the minority charge carriers? Tell me that for the N-type semiconductor, the majority of the charge carriers are what? Electrons, right? Because N, which means negative, right? And P, which means positive. So negative is always due to electrons, right? And the minority charge carriers in the N-type will be what? They'll be holes. Similarly, for the P-type, what will be the majority charge carriers? Holes, right? It will be opposite to that of your N-type semiconductor, right? So P-type and N-type, they are exactly opposite to each other, right? So if in N-type, the majority are electrons and minority are holes, in the P-type, it will be inverse, right? So majority will be holes and minority will be electrons. So these electrons and holes, they are known as the charge carriers, right? So if somebody asks you, how can you define that what is a charge carrier? Then what could be your answer? Can this move? Holes and electrons? Yes, right? We are considering the holes and electrons as the mobile charge carriers. They can move because, see, holes ideally cannot move, but then electrons are taking place of that hole, right? So somewhere else the hole is getting created, right? And the electron can come over there. So ideally we consider that there is a movement of the holes and the electrons. So just keep it simple that we call them as the mobile charge carriers. Mobile. We carry our mobile with us, right? So it can move. But previously we had the phones which had the wire, so we cannot move, right? So similarly, these charge carriers, they are mobile, which means that they are free to move. Understand, right? So when we are bringing the P and N together, there were two phenomena which was happening. We discussed about two different things, which was what? One is when we bring it together, what happens? Diffusion. You heard something about diffusion, right? So when these two we bring together, there is something known as diffusion. And then also you studied about the electrostatic force, right? So diffusion is like when you are bringing it together, some of them will try to go in this side, some of them will try to go on that particular side, right? But then ultimately it will come into the equilibrium. And because of that, what will happen is that no more charge carriers will be allowed to cross the boundary, right? We saw that there is a wall which is created in between, right? So over here, initially we have all the electrons in this region as well. But then what happens is, see, initially till here, all the electrons will be there, and on this side, all holes will be there. But then ultimately, because of the diffusion, what happens is that no more, the electron, because it is a pentavalent impurity, the electron will go and fill the space of that in the trivalent impurity, right? When that starts to happen near the junction, we can say that this kind of charges are getting placed over there. And because of that, what happens is, so this holes and this electrons, they are mobile charge carriers. But the charges which are present over here, they are no longer mobile. They cannot move. All of you agree with me, right? Why? Because over here, this would have formed the covalent bonds. There is no more, they cannot really, if there is a covalent bond, they are not free to move. Understood, right? And just think in this manner that why it is not allowing any more electrons to pass in this region is, we saw that because of the electrostatic force, that when we have negative negative, positive positive, and positive negative, so when we have negative negative, what happens? They repel, right? And when we have positive negative, it will attract. So just think about it, that when there is a negative charge which is accumulated in this region, do you think that any more electrons will be able to flow through this region? Because what it will do is this negative charge, it is going to push the electrons because it is going to repel. That is negative and negative, yes or no? So this negative, it is not going to allow these electrons to pass in this region. Similarly, if you think hypothetically, then this positive charge, it will not allow any holes to flow in this direction. Usually we never consider the movement of the holes. We usually consider the movement of the electrons, right? Electrons are the one which can actually move. Holes cannot move, right? So electrons are not in a state to move. So this particular region which is there at the center, that is known as which particular region? We called it, we gave one term to this region, which was what? Depletion region. Why depletion? Because it is depleted of any mobile charge carriers, which means that there are no more holes or no more electrons which are present in this region. All of you agree with me?
Yes, sir.
Right? That why it is known as a depletion region. Right? Understand?
Mobile charge in the region.
Yeah. So, see, what is the mobile charge carriers? This electrons and the holes. They are mobile, they can move, right? But now there are no more electrons and holes which are left in this region, right? And that is why this particular region is known as depletion region. It is depleted of any mobile charge carriers, which means that there are no more holes left or no more electrons left, right? So this creates a wall. Because of that, no more charge carriers are allowed to pass through. Hope you're getting now, right? So this is depletion region, DR, right? Understood? So now, what we studied after this, what we did now, we studied two different things by connecting a battery. Yes or no? We connected a battery to it, and then we studied two different things. One was forward bias, another one was reverse bias. So in which particular condition we say that the switch will be on, because this acts as a switch. Yes or no? Yes. Right? So currently in the equilibrium, because we are not connecting any battery to it, right? So when we connect a battery, can you try to tell me that when can we say that this PN junction is forward biased? Forward bias, which means what? The switch is open or closed? Switch is closed. Very nice, right? So current will be able to flow through it. Why it allows the current to flow through it? So we discussed yesterday that what exactly happens. Now tell me what will happen because of this. If I connect the positive of the battery to the P side and negative of the battery to the E side, what will happen? Tell me. When we increase the voltage. And you should know that positive, positive, negative, negative, positive, negative. So negative, negative and positive, positive, positive will repel. So over here negative is connected to negative. So what will happen to the electrons? Electrons will start to move because this negative charge is going to push, right? And this side we are connecting positive. So don't you think that this electrons will be more attracted to this positive? Because positive and negative will attract each other. Hope you are getting, right? So from one side somebody is pushing and other side somebody wants to collect it. So we are increasing that kind of thing. So as a result we can say that the electrons will start to flow. So we can say that the electrons will be moving in this direction, which is anti-clockwise. What will be the direction of the conventional current? Conventional current I will be in which direction? It will be in the same direction as electrons, or it will be in the opposite direction? It will be in the opposite direction, right? So I will be in the opposite direction. So electron is in this direction, but current is in the opposite direction. Hope it is clear, right? The next is what happens, and basically we can say that when we connect it like this, this particular state is known as forward bias. Understood? So what is the condition for reverse bias? What should we do now? If I want to make it into reverse bias, what is the change that I need to do? We connect the battery in opposite manner, right? So now the negative will be connected to positive and positive will be connected to the negative. So because of that, what do you think will happen? What do you think will happen? Tell me. Look from this, because now the positive is connected to the negative, and we actually want the current can only flow if this electrons actually pass through this and it enters at the other side. Will that happen over here or not? It is not going to happen, right? Because you are connecting a positive to the negative. So electrons will move in which direction over here? It will move in this direction or that direction? Towards the positive side. Yes or no? Because it attracts. Good. Right? So when this is happening, we can say that this depletion region will go wider. Yes or no? Which means that we are increasing the barrier now. In the previous case, we were decreasing the barrier. In this case, in the reverse bias case, the barrier is getting increased. So when the barrier gets increased, the current flow will decrease. I mean, there will be no current flow across this particular device, and this is known as reverse bias. Clear? So this is reverse bias now. Now, if we take an analogy with a switch, so forward bias, can we consider that the switch is closed? Why? Because if you think like this, just consider that this is PN. Very simple now. Because I am connecting my positive with the P type, you can just check from here, right? When I connect my positive with the P and negative with the N, can I say that because the current can flow easily, I can say that my switch is closed? Understood? If I connect it in a reverse bias condition, my switch will be open. No current can pass through. Hope this is clear to all of you.
Yes, sir.
Right. So now all of you know what is a PN junction, right? So this junction between P and N, that is known as a junction. Understood? This region, it is known as which region? Depletion region. Why it is known as depletion region? There is no mobile charge carriers present. Mobile charge carriers. Understood? What are mobile charge carriers? Holes and electrons. They are considered as the mobile charge carriers, which are not present in this region, and that is why it is known as a depletion region. So our task is to overcome this depletion region, then and then only the current can flow through that device. If the depletion region increases, then no current can flow. Clear to everyone? Right, so this is PN junction. Now we already know what is a P-type semiconductor, what is N-type semiconductor, and then we also looked at this MOS. What was MOS? Metal oxide semiconductor, right? So let us have a quick revision of what was MOS.
Sir, before we go to this, I have one question to ask.
Yes, I know.
When the anode is connected to the N type and the cathode is connected to P type, will the light function?
Let's do that. Now you said anode and cathode, right? So let us first understand what is anode and what is cathode. So usually just keep it very simple. Anode is something which is positive and cathode is something which is negative. Keep it very simple. So over here, now which one will be anode?
Plus.
So this is plus, right? So this will be your anode terminal and this will be your cathode terminal. Simple. This is plus and this is minus. Now you only will be able to tell me, right? It is very easy now because you just got confused by the terms. That's all. Anode is always a positive terminal and cathode is always a negative terminal. Now you already know that where to connect what. Understood? So now if you connect your anode to the positive, tell me what will happen, and let us say that we connect a LED over here. Will this glow? It will glow, right? Why? Because this is forward biased. Yes or no? Because now we are connecting the plus to plus and minus to minus. And that is what we discussed, that in forward bias condition you connect the positive to the positive and negative to the negative. So the switch will be considered as closed, right? Because of that only the current will flow. If the switch is open, will there be any current flow? Can current flow? She is saying yeah. She is in a mood to dance today. I don't think she's in a mood to study today. So we just need to think about it, that the LED can only glow if there is a current flowing. So current, it should start from here, and when it ends over here, then and then only the LED can glow. If there is any break in between and if the current cannot reach the other terminal, then we can say that it is open circuit, which means the switch is open somewhere and there is no current path to enter into this terminal. So when it starts from one terminal, ends at other terminal, we can say that the circuit is a closed circuit. Understood? But instead of that, if I am connecting it like this, now tell me what will happen. Positive is connected to, this is negative or positive? Negative, right? And this is positive. So when positive is connected to negative, what will happen? This is considered as power forward bias or reverse bias? Tell me. Reverse bias, right? So when it is reverse bias, the switch is open or closed? Open. Very nice. So when the switch is open, let us say, so if I consider that if the switch is open, will there be any flow of the current to the LED? There is no current going to the LED. So in simple terms, just think of this wire which is coming from there. What happens if I cut the wire? Will there be any connection going to the TV? Nothing. It is simple like that itself, right? So if I'm keeping a diode over here in between, which acts as a switch, when I close it, the TV will start. If I turn it off, the TV will, because the current going from there, it will not go to the TV. It is as simple as that. Clear to all of you? Right? Any other doubts? She has studied. She will get full marks today. 10 out of 10. So some terminologies, I think, when you start reading, then you get to know some more terminologies like this, right? But there is nothing to get confused. These are just the other names of those terminals. So let me know if you have any other doubts. Yeah? So should I go ahead with the MOS? Okay. So in the metal, oxide and semiconductor, Now, what we were discussing yesterday is first we need to understand that why should we study metal, oxide and semiconductor. Then just understand that yesterday you studied all the gates, AND gate, OR gate, NOT gate. Yes or no? So ultimately all this logic gates could be realized using this MOS device. That is why we understand how this works, right? Because all the logic functions which goes into the chip which is present in my laptop, on my smartwatch, in my phone, on the TV, everywhere there is a integrated circuit. An integrated circuit is having the transistors, and the transistors look like this. I mean, you won't be able to see with your eyes because they are in terms of nanometers. Just because we want to understand, I'm drawing it so big. Otherwise, even if you see with a microscope, you cannot see because it's a microscope and the size of this device is in nanometers. So nanometers is even smaller than the microscope. So you'll not be able to see in microscope either. It's that small. So in this much of the size, let us say just like this size, they are putting billions of transistors. How many? Billions. So more and more number of transistors if you put, you can put more functionality and features to any device. See, if I am using iPhone, right? iPhone 16, iPhone 17 will come. iPhone 17 will have more functions and more features. That is how the company will make more profit. Otherwise, if it is having the same function and same feature, why would somebody buy a new phone? Nobody will buy a new phone, right? If you go and buy a TV, you will look, oh, is there something new in the TV which is not there in the old one? Then only you're going to buy a new one. Yes or no? So how do you think that is possible? Because see, the size of that device cannot be bigger, which means that there is a restriction in the size. The chip size cannot be. So let us say that this is your phone, right? Let us say that this chip size is fixed. You cannot have more than this size available. So then, what do you think? How you can put more functions and features to that? If I do that, I can put more number of devices in this small area. Are you understanding? Yes, so let us say that in iPhone 15, I'm just hypothetically telling, I'm not going in billions, but let us say that in iPhone 16, we have 100 of these devices. Now, if iPhone 17 comes, we may need that this number should go to 200, double. How to do that? Because we are not allowed to increase the size of it. So then what should we do? We need to make the individual transistors compact. Yes or no? Right? And that is what we are going to learn later, which is the fabrication of MOSFET. How to fabricate this device. Right? How to fabricate this device. Right? It is not that easy process to fabricate it. And you are patterning it. Patterning, which means what? That let us say that I have something like this. Now I want that this particular thing should have a bump, right? Or just take your house itself, that you want somewhere some kitchen to be there, your drawing room to be there, your bedroom should be somewhere there. So just from the scratch, now you need to start building your rooms, and similarly it also needs to be planned that where exactly you want to put this. And then you are realizing all these functions like AND gate, OR gate, NOT gate, because that leads to it gives the logic to it. Right? And how this logic comes is through these transistors, how they work. So you do the programming of these devices, and then accordingly this hardware will be realized. And then once that is done, then you can send this particular file for the fabrication, and they are going to fabricate the chip for you. So this, before any phone is made, the first and foremost thing is that you should have your chip ready with you, which should be completely tested. If it is not tested, tell me what will happen. Let us say if iPhone 17 comes into the market, right? If they haven't tested the chip, and if something goes wrong, what will happen to the company? Because nobody is going to buy the phones. And you should know that whenever they are giving this chip for fabrication, it costs so much to the company. So if one product fails, it is a big loss to the company. And moreover, don't you think that if you have a company, you launch a product, and if that product fails, what about your market value in the customers? They will think that, oh no, this company is not reliable. You're not going to buy that product next time, right? So none of the company can afford that particular thing. They need to ensure, so they tell that, okay, you have 10 years of warranty. So when can they say that you have 10 years of warranty on something? Because they have rigorously tested everything. So when you design something, you test as well that, okay, it is going to work in any condition, right? And that is why they can claim that you have this much of warranty on that, right? And that is why these companies charge a lot, because they will hire very good people, right? Not just the engineers, but even the non-engineering background students they are hiring, they will take a test for them. So if they are having a very good knowledge, you go work there, you will also be again trained according to the company standards, right? And when you work, you will work in such good manner that there'll be no mistakes that should go in designing, verification, packaging of this kind of chip. And that leads to a very good product in the market, where nobody will have any complaint, right? If there is any complaint in the product, why would you even buy it? Nobody will buy that. Yes or no? Right? So some of the Chinese products, because if you think about it, if you compare, then Apple costs somewhere around 1 lakh rupees. Some of the same Chinese phones, right, which gives the similar features and the functions, they cost not even half the price of that. You may get it for somewhere around 30,000 or 25,000 as well. But then, do they give any kind of warranty? Nothing. If it goes wrong, it's wrong, because you're not paying enough for that. And why you don't pay, or why the company is not charging, is because they haven't done the tests which are needed. And in that particular case, there is very good chances that the product will fail. They don't pay to the engineers enough, like what these companies are paying. So that is the main reason why some of the products are expensive and why some of the products are cheaper. Hope you're getting that how this electronic market works, right? So that's why they say that the Chinese products, if it runs, it will run forever. If not, it may not even last till night, right? Yeah, because they haven't done rigorous testing of those particular products, right? They just make it and just sell it in the market. Yeah, cheaper, yeah. People buy them because not everyone can afford Apple and Samsung phones. But then there is no guarantee in that. So if you're spending 25,000 for a mobile phone, there is no guarantee that it is still worth it and it will work for certain years. That's the problem. But if you spend 1 lakh, if the Apple is telling your phone is going to last for 5 or 6 years, it will last for that long. You will not have any complaint for that. So rather than spending 25,000 per year and then you have to change the phone, it's better just to invest in something which will last longer, right? I'm not a marketing guy of Apple, but it's just I'm saying, right, that usually the company prices work like this. Understood? Right? So everywhere, if you see anywhere, right now, a lot of autonomous cars are coming, right? Autonomous cars, you don't even need a driver. The car will run automatically. So just think about it, that when it is running on the road, if a pedestrian is crossing the road, you just imagine that the car needs to first sense that somebody is there. Now that signal will go to the car. The car needs to process that data and need to take a decision that, oh, I need to brake. Now just think of the time duration. Fraction of seconds. If this process is not done fast enough, then the car will run over that pedestrian. Hope you're getting. So all these capabilities is only possible because of the technology, and that is semiconductor technology. Because you're making such powerful chips, which is this integrated circuits. So this integrated circuit works as a brain for any of the electronic products nowadays, right? They can do a very good processing, right? Very fast processing. So as soon as the data goes into the chip, it processes the data, it takes a decision and it tells that, okay, you break now, right? So there's so many things it could do, and that is only possible because of excellent design of this integrated circuits. That integrated circuit get its brain because of the Boolean algebra that you learned yesterday. This AND gate, OR gate, NOR gate, right? There are a lot of other gates which are capable of doing different functions, right? So you program it accordingly, and then you get the things to work properly. Clear? Right? So for MOS, now there were two different things that we studied yesterday. The first thing is we want to turn on the device. So if we want to turn on the device, what was the process? And out of this complete structure, the one which I have drawn over here, which particular portion shows this region? Can you try to map it? Can you try to map? So it was the center portion, yes or no? This one. So this is your metal, this is oxide, and this is your semiconductor. And this exact center portion is drawn over here. So why should we study that first? Is because I gave you an analogy as well, that you have an overhead tank, right, which is filled with water, which is on this end. Understood? So let us say that we have an overhead tank, right? This is connected to the source. Now this gate acts as a nozzle of your tap. When you open it, then only this water can enter from here, and it should flow from here, and it will be collected. There is a bucket over here. So this water should enter over here. So just think about it, that it needs to cross this region first. Then and then only it can enter into the bucket. So that is what we discussed yesterday, that what should we do that this thing gets closed. So what should we do? What did we discuss? So the substrate is of which type? Substrate is of which type? This is substrate, right? So substrate is of P-type, and P-type is having majority charge carriers are holes, and minority charge carriers are electrons, right? So we discussed that because this is also N, this is also N-type region. So we need to bring the minority charge carriers, which are electrons, in this region, so that we can make a complete N channel over here, and then only this water can go from here all the way from here and into the bucket. Yes or no? And we just replace this water with the electrons in our case, and that is why we need an N-type over here. So if you try to bring electrons over here, we consider this as a complete channel now. Hope you understand. Right? So in order to do this, what should we do? What kind of voltage can we provide? Now you know that how to attract the electrons. What kind of voltage to give? Tell me. Opposite charges attract each other, yes or no? So if you want electrons to come over here, what kind of voltage you should give at this terminal? Tell me whether you should give positive voltage or negative voltage. You will give positive voltage. So when we give positive voltage over here, it will attract the electrons which are present in this region, right? Because the P-type, I told you that the P-type will have So in the P-type substrate, we have the majority charge carriers which are holes. That is why I denoted this by plus. And the minority charge carriers are electrons. So we want the minority charge carriers to come and accumulate in this region. So this region will still be filled with positive. So initially your electrons will be scattered like this, but when you start giving positive voltage, all the electrons will be attracted, and we want this to be accumulated in this region. So why only it is getting accumulated in this region and not over here or over here? Because you are just giving the voltage in this direction. Just imagine like this. Understood, right? So you are giving a positive voltage at the gate. There is a metal layer over here and there is oxide. So oxide layer acts as a insulator. Insulator, which means it will not allow anything to pass through. So when you apply a positive voltage, all the electrons will be attracted, and why it will stop over here is because insulator will not allow them to pass through, because it is a bad conductor of electricity. Yes or no? So just consider your electrons as a current. So the current is flowing in this direction now, but it cannot pass through now. So oxide acts as a closed switch. Just understand. Right, it will not allow anything to pass through. Clear? So this is your, which kind of MOSFET? What kind of channel we are creating over here? N type or P type? The channel is N channel, right? So the name is NMOS or PMOS? NMOS, right? We discussed this yesterday. NMOS. MOS is your metal oxide semiconductor, right? And there you're creating a N channel in this region, and that is why the name is given N channel metal oxide semiconductor. Hope it is clear to everyone. Right? So this we get by providing a positive voltage at the gate terminal. Right? Now once the channel is formed, the next thing what we will do is how to now start the current to flow through it, because this was the first step. We just made a channel. We haven't yet started the current to flow through it. So for the current to start flowing, we need to give up a voltage at the D end as well, drain end. So this G denotes a gate, S denotes a source, and D denotes a drain. So now, after creating a channel, the device is now on. Once it is on, you will keep that voltage as it is, because you still want that the channel should be there. As soon as you will remove the voltage from here, what will happen? Tell me, what will happen? If I remove the positive voltage, what will happen? Will the electrons remain over here? Or it will fall back? Again, the question, just understand this. That when I'm giving a positive voltage at this end, right? So when we give a positive voltage, the electrons are now remaining at this location. Understand? But if I remove this positive voltage, what will happen to these electrons? Will it still be there? It cannot stay there, right? It was only staying there because a positive voltage was holding it. If I remove that voltage, the electrons are going to fall again, right? And it will again be like this. Understand? So the condition is that I always keep the gate voltage which is positive, so that the device always remains in an on state. Once that is there, now I will start giving the voltage at the drain end, so that the electrons can enter from the source, it will go through here, and it will be collected at the drain end. Hope it is clear. So these are the two different things, two different voltages we need to give to the MOSFET device. Is it clear? Any doubt? Please ask me if there is any doubt. So now think in this manner, that instead of NMOS, if I now tell you that this is PMOS, so what will be the change? If this is PMOS, so P indicates what? P indicates what? P channel, And P channel will be formed with what? Holes or electrons? Holes. And whatever we are forming the channel, they are minority charge carriers or majority charge carriers? Tell me, minority charge carriers or majority charge carriers are present in the channel region? Minority charge carriers, right? So, because in here we saw that for p-type, your holes are the majority charge carriers and electrons are minority charge carriers. So similarly, if you go for PMOS now, so first of all you should think about it, that what should be your substrate. The substrate will be of n-type or p-type? Why n? How you decided that it is n? Because you want to make a channel which is formed of positive, right, which are holes, and holes will be minority charge carriers. So what will be the majority charge carriers? Again the question, we are talking about PMOS, which is P channel. So channel will be formed of holes or electrons. That is the first thing, first question. Because this is P channel. P is always positive and positive is holes. N means negative, negative is always electrons. Keep it simple. So now we want the channel to be formed of P, which are holes, and the channel is always formed from minority charge carriers. So in which type of substrate you have minority charge carriers which are holes? P-type or N-type? N-type, right? So when you have N-type substrate, your majority charge carriers are what? Electrons, right? And the minority charge carriers will be holes. So now what kind of voltage should we give so that the holes get accumulated in this region? What should we give? Now we want our holes to be attracted near this channel region. So what kind of voltage to give? Negative or positive? Negative voltage, right? When we give negative voltage, the holes will come and accumulate in this region, and the negative voltage is going to hold it. So now the channel is there. Once the channel is there, we again start giving the voltage. Because of that, the current will start to flow. Hope you're understanding that how your MOS device works, right? So this is both the PMOS and NMOS, and this PMOS and NMOS constitutes your CMOS, which is complementary metal oxide semiconductor. This is very important for you to know, right? So now the symbol, so this is the symbol for your NMOS. See, so let us understand that what does this arrow indicates. This arrow indicates something which will be explained from this region. So let us say for NMOS, electrons were going upwards. For N-channel MOSFET, yes or no? Let us consider this one as NMOS, right? So for NMOS, this is P-type substrate. Understood? If I want electrons to be over here, I will apply a gate voltage. Yeah, sure. So what I did, I applied a positive gate voltage. When I apply a positive gate voltage, the electrons, which were initially like this, it started to move upwards. Yes or no? So similarly, just think about it, that this is gate. Just understand this. This is gate. We consider this as a metal in the center oxide, and then this is a channel region. Understood? So electrons are moving towards the channel. Yes or no? That is why this arrow indicates inside. So the symbol, you should understand that why the symbol is like this. In the other case, which is PMOS, you are bringing what? You are bringing holes. Yes or no?
Yes.
For P channel MOSFET, you are bringing your holes and the electrons will be pushed downwards. We'll see over here what will happen. For PMOS, what will be the majority charge carriers? Electrons will be the majority charge carriers because the channel is formed by holes. Right. So substrate will be of N type, which is electrons. So the electrons are, when you give a negative voltage, the holes will be pushed upwards, while negative and negative, they repel. And so the electrons are moving in downward direction. So over here, can you see that the arrow is in the downward direction? Getting or not? See, this arrow is indicating the direction of the electrons. So for NMOS, the electrons are moving upwards or downwards? Just think about it. For NMOS, where does it going? Going upwards or going downwards? It going upwards, right? That is why it is in towards the channel. So consider that the channel is over here. Understood? So electrons are going towards the channel, while in case of PMOS, it is P channel. So don't you think that the channel is formed with holes for PMOS? Look over here, because you are giving negative voltage. So so channel is formed of holes and the electrons will be pushed downwards. Yes or no? That is why over here you can see that the electrons are moving downwards while the electrons are moving upwards in your NMOS device. Hope it is clear. Right? So this is your NMOS and PMOS, and after the tea break we are going to see the fabrication. How to fabricate this particular device. Right? Fine, let's have a tea break. So after the tea break, if you have any questions, we'll first try to clear the doubts you all have, and then we'll go for the fabrication. Right? So you should remember the symbol, because usually the symbols are used for your NMOS and PMOS. And then one more thing I'll just tell before we go for lunch break is, the third is your CMOS, which is the most widely used device, which is a combination. C indicates complementary. Why it is complementary? Because it is made up of both NMOS and PMOS. Right? So it looks something like this. This is the most important thing. So this complementary metal oxide semiconductor is made up of both NMOS and PMOS. So we cannot really jump to CMOS unless and until we have understood your NMOS and PMOS, and that is why I covered your NMOS and PMOS first. Now when we bring it together, how it works, that's a completely different thing that I don't think I'll be able to teach at the moment. And you will not get it as well, right? It's a little complicated, but then we will at least understand that how to fabricate your NMOS device and the PMOS device, right? So, and that is where we'll stop, right? Fine, okay, let's have a tea break. Because you will not anyways remember a lot of the terminology, but at least understand the process. That what is this process about, right? So for NMOS transistor, now you already know what is an NMOS transistor, right? Yes or no? So what is an NMOS transistor? What do you think will be the substrate? Let us first start writing it. What does N indicates? All of you know, you should tell her. What is N? N indicates what? Negative, right? N. But then what is the full form of this one? This is N channel. Metal oxide semiconductor, right? So that is what we are trying to learn over here, fabrication of NMOS transistor, right? And when we studied about NMOS, which is N channel, so we should first think about what should be the substrate. Will it be a P-type substrate or N-type substrate? Tell me.
Sir, one question before
Yes.
we go. Can you explain to them what is fabrication first?
For that itself, we need to study this and then we can go to that one. That is the first step. That is the first step. So tell me the substrate that we use for this N-channel metal oxide semiconductor. What type of substrate should we use? You are writing N-type or P-type, right? And then we are creating a channel. So what should be the substrate that we use? Tell me. Substrate should be of P-type or N-type. Channel we are forming using what? Electrons or holes in NMOS? Electrons, right?
Yes.
And electrons are minority charge carriers or majority charge carriers? Minority charge carriers. So majority charge carriers will be holes, and holes, they are of P-type or N-type then? P-type, right? So the substrate will be? Substrate will be? P-type, right? So that is the very first step that we start the fabrication from, right? So go to the next one. So see, the very first step itself is your silicon substrate, right? Which is P-type. Why? Why P-type? Because we are currently understanding the fabrication process of NMOS. If we are discussing the fabrication of PMOS, then the substrate will be of which type? This is for NMOS, for PMOS. So first I'm talking about the substrate. So for NMOS, if we use P-type substrate, for PMOS we'll be using N-type substrate, right? It is exactly opposite as I was telling, right? So for PMOS, it will be N type of substrate. Do you understand? And also I'm drawing the final diagram that we should get after all the fabrication steps are done, so that you keep on checking that which particular layer we are forming. So if I write down like this, we are discussing about NMOS or PMOS. Just by looking at it, what do you think? This device is NMOS or PMOS? This is a NMOS. Why? Because your substrate is of P-type, and your channel which you are going to form, that will be N channel, which are made up of electrons. So first step is we take a substrate, right? The next what we do is the complete surface we will pass it for oxidation, right? Because the silicon dioxide layer, can you see this SiO2? So this silicon dioxide layer, that is nothing but an insulator. So now you should know what is an insulator. What was an insulator? Which will not conduct any electricity, right? So now you should understand that for such device, why we need insulators are because at every layer we want that there should not be any short circuits. And wherever we don't need any short circuit, we need to keep an insulator in between. So always if you come across the silicon dioxide or thin oxide layers, these layers acts as insulators. Understand? Right? So I'm going to tell you that which particular layer acts as insulator, which particular layers acts as conductors. Understand? Right? So we will first start with the silicon substrate. Now the entire substrate goes into the, let us say that there is a room, right? This wafer is kept in there. We put the substrate in there, and then there is an oxidation, so a lot of oxide, oxygen, right? We put it. So what it is going to do, it is going to deposit on the top of that. Are you understanding? What will happen? It is something like this. So initially just consider that this black portion, right? Just the black portion, that is a silicon substrate. Now the top portion, initially it will not be there. But when I put this black portion into the room and I put a lot of oxygen on there, there'll be an oxide layer which will be formed on top of that. So that I'll get this thick layer of silicon dioxide on top of this substrate. So you're understanding that initially we'll only have the black portion. In the second one, you'll be having the top layer, which is this white portion, which will be created on top of that. Are you understanding? Now what is needed is, can you see this portion? That is nothing but this too. So now what is needed is, because this silicon dioxide is a complete layer. Now do we really need anything in between? Because currently I only need on these two sides. Hope you're understanding. So somehow I need to remove this. Yes or no? If I grow something, I still need to remove it. So then what should I do in order to remove it? So that is what we are going to discuss next, right? And this, after growing, whatever we are removing, that itself is known as patterning or photolithography. So using this photolithography process, we can actually pattern this kind of patterns on the top of the substrate. You understand, right? So let us try to understand that. I'm gonna carrying a carbon. So just think about it. This is an oxidation furnace where this substrate will go, right? And based on that, a silicon dioxide layer will be formed on top of it, right? Now the next step is how to get rid of the center portion, because currently I only need the two on the side only, right? So oh Now understand over here what we are doing, right? So how to get this? So think about it. There's a black portion, right? Now this layer, that is the white layer. Now what we are doing is, this is a photoresist. So we put photoresist on top of it, which portion we need to keep, right? And this portion which we want to remove, we are not going to put any layer on top of that. So just look at it, that this additional thing, that is known as a mask, right? So I'm putting a mask on top of that, and this portion I do not want. So here, after putting this photoresist mask, I'm going to pass it through the ultraviolet radiations. So because we have a lot of girls over here, are you guys using something to do your nails? When you put this nail, are you putting that under ultraviolet radiation or something like that? Do you have that over there? Or I'm not too sure. Because here they do a lot, like the artificial nails. You know, with the artificial nails, what they do is that they will do the coloring of the nails, and then what they will do is that the girls will put it under UV, and then that portion will get hardened, whatever the things are doing. So same thing is over here as well, right? So that is what is happening. So now, let us say that you want to keep that nail polish in this region, while you don't want the nail polish to be over here. So what you will do, that you will use a mask on top of it, right? And when you will put ultraviolet radiations, this portion will get hardened, right? And this portion will become soluble. So when you put it under chemical, I mean when you pass it through chemical, what it will do is that it will not allow this layer to interact with that chemical, because it is covered by this. Hope you're understanding. Right, I'm covering it with that portion, so when I put some chemical, that portion will not be affected. But because this portion was not covered by any mask, when I put it under the chemical, it can easily be removed from this portion. Are you getting? So I'm basically trying to save these layers by using this particular photoresist mask. Understand? So the photoresist mask is going to prevent the oxide layer to react with the chemical that we are going to use, right? So based on that, so similar thing. So what we did is, we started with the layer which was complete. The final we get is like this. We removed the center portion. Did you see that? Right? So previously it was looking something like this. And now it is looking like this. So now you understood that how we get from this to this. Yes or no? Right? So over here we put the mask on these two sides, while the center we kept it open. And then we use the chemical which will get rid of the silicon dioxide. So whatever surface was exposed, it was not covered with the mask, that will become soluble and you can easily remove that. Hope it is clear to everyone. Right? So after the silicon substrate, the next layer that we are using, that is a thin oxide layer. You will see in the final one that why this thin oxide layer is needed. So this thin oxide layer is also known as an insulator. So I'm going to write down that what particular layers. Right? So every time we put some layer, if we want to pattern it, we'll pattern it using the photoresist itself, right? Now let us understand one more process, which is the photolithography itself, which is the patterning, how we do that, right? So photolithography is usually a method which will be used to pattern at every layers that we need to form on the top of the substrate, right? Because this MOS transistor, you can see that there are a lot of multiple layers over here, right? We have substrate, then there'll be thin oxide layers, there is also an oxide layer over here, then there is a metal layer over here, right? How to come up with these different layers? Then we first need to come up with a complete layer, and then we need to take out those layers which are not needed. Right? So at every stage we need to deposit and we need to take it out. We need to deposit, then we need to take it out. So whatever we want will remain over there. What we don't want, that will be removed. Are you getting, right? And that will be done using the photolithography process. Now photolithography also has two different methods. So this is very easy to understand if you consider about your nails, that how you are doing. So just think very logically. You have your substrate, right? This is a silicon dioxide layer. There are two different portions which is given. In the first one, what I'm getting is, I'm getting this two portion which is left after I use a photoresist. So from initial layer, if I want to get rid of the center portion, I am using a technique which is known as positive photoresist. And the second one, if I apply like this, and if I again put it under the UV, right, I'm only getting this particular portion which remains, right, and the rest of the portion will be removed. So then what exactly is the difference between positive and the negative photoresist? Because you need to think in that manner that if I'm using a mask, photoresist mask, if I put it under UV, either that mask will be hardened or the mask will become soluble, right? So which portion will make the layer which will be soluble and which portion will make it harden? Can you try to identify from this one, this process? See, so just look at it. This is a silicon substrate, right? This is a silicon dioxide layer. This is a photoresist. Now the photoresist could be of two types, either positive photoresist or negative photoresist. Now you are using a mask on the top of it. So if I'm putting a mask like this, only the UV radiation is going at the center portion, if you just look at it. But if I use a positive photoresist, I'm getting a pattern like this. And if I use a negative photoresist, I'm getting a pattern like this. So what do you think is the difference in the photoresist? Which becomes soluble and which becomes hardened? Just think about it. Anyone? See, when you put something on your nail, right, you don't want that to go, right? You want that to stay. You paint your nail. Let us say you make a very good drawing or something like that. You put something to make it look excellent. Now you want that to stay there. And that is why you are passing it under UV.
Yes.
So that thing will get hardened, yes or no?
Yes.
Or is it become soluble? It becomes hardened. So just think in that manner and tell me that which process is a positive photoresist and which process is a negative photoresist. So the process of putting a nail under the UV, that's a positive photoresist or negative photoresist? Just think about it, right? I mean, that is the best example I can give, considering there are a lot of girls in the class. You can totally relate. What do you think?
Same, positive or negative?
Positive photoresist. How many of you say positive photoresist? What do you think? I mean, you should understand, right? Don't just raise your hand. It's a clear process that why the positive photoresist, it is called as positive photoresist. So, in positive photoresist, let us understand that what is happening. See, there was a layer, right? When you put mask. Now, when you put UV radiation, this center portion, it becomes what? Soluble, yes or no? This portion got, this photoresist got soluble, which means that that is no longer there. And if it is no longer there, now when you pass it through the chemical reaction, so that because you want to remove this, you want to pattern this layer. You are not interested in patterning this, that is used to pattern the green layer. So you are using a red layer to pattern the green layer. So just understand that from this you want this, and this will only stay because the red layer is protecting it. If the red layer is not on the top of it, if you pass it through the chemical, this layer will not be protected. It will be gone. Now can you try to think that what is the difference? Now you should think about it. Take your time, it's okay. Because photolithography is like the most important thing you should know about. Because at every step you are using photolithography to get the required pattern. If you understand this, rest of the thing all just follows. That's all. So did you understand the process or not? At least, what is the difference? This becomes, so when it is exposed to the UV radiations, this becomes soluble, this portion, it is removed. While in this one, because the mask was over here, right? And when you put the UV radiation, this portion becomes hardened, while this becomes soluble. So the negative photoresist becomes hardened when it is exposed to the UV radiation, while in case of positive photoresist, the photoresist becomes insoluble. I mean, it becomes soluble, and so it will be removed. Hope it is clear. Right? So you only need to understand that whatever portion you want to keep, you need to protect it using the photoresist. Because photoresist will not allow the silicon dioxide layer which is underneath that to react with the chemical etchant. Etchant is something which we use to remove the silicon dioxide layer. Understand? So the red portion on the top will not allow any chemical reaction to take place. Right? So it is protecting it basically. Say when we are staying in our house with our parents always protect us. So this red layer is like our parents who will protect us. Understand? If the parent is not there, then we're vulnerable, right? Anybody can come us and harass us and do whatever they want to do, right? So currently the red layer is something like this. Is it? Are you all understanding, right? So photoresist, positive and the negative, it should be clear to all of you. So in the positive photoresist, the photoresist becomes soluble when it is exposed to the ultraviolet radiation, while it becomes insoluble when it is exposed to the ultraviolet radiation. Clear? So
Negative is
insoluble because it gets hardened, right?
yes.
Just understand that when you are exposing it, only this portion remains. While in this case, this portion is remaining while the center portion is not there anymore. If you have any doubt, feel free to ask me. Do you want me to repeat? Any question?
Please explain again.
Okay. See, so Paul, this photolithography is a process to come up with a pattern on our semiconductor material, right? Or we can say NMOS or PMOS that we want to achieve. So at every layer, we need to do this kind of patterning. So just understand one thing, that we have this green layer on top of the silicon substrate. Now this green layer we want to pattern. So if we want this kind of layer or this kind of layer, now we need to decide which particular photoresist to use. So first we should understand that what is a photoresist, right? So what we will do is initially we will put the photoresist over here, right? So let us say if you want just the center portion to be there. So as I already said that the red portion, which is photoresist, it acts like our parent. This silicon dioxide layer is the children, right? If some gangster come from outside, they want to shoot you, then your parents will not allow to do that, right? So this photoresist layer is protecting it, right? Here there were no parents, so they took the son or the daughters, right? But over here the son is protected or the daughters are protected, right? Similar to that. So how that happened is the complete red layer, when you are exposing, because this black thing is like a mask. So how does the mask works? Just understand that you have something like this, right? 2 layers. Now when it is like this, it is completely covered. So there is a layer underneath, right? When you put a UV, it will not go. But now we are clearing it out. So this 2 black layers are something like this, which will allow it, right? The UV to pass through.
Yes.
So you just need to understand that when the UV touches the photoresist, which particular photoresist becomes soluble and which one will become harder. That's all. So which layer you want to keep and which layer you want to remove, based on that you will be using the photoresist. It is as simple as that. So wherever there is no photoresist, that silicon dioxide layer will be gone whenever you are using a chemical which will get rid of that silicon dioxide layer. Clear? Still any doubt or not? Or is it clear?
Telling me yes and no, just looking at me.
So teacher is going to explain. Teacher, please come. Maybe they only understand what you teach. Huh? Something like that. Fine. So at least it is, the basic idea is clear, right? So what is the function of the photoresist? So at every layer we need to use some kind of photoresist so as to get the patterning. Just keep it very simple, right?
In order to make a chip, we need to make a pattern, right?
Yes.
Right?
Yes.
That's basic. In order to make the chip, the phones or all those, we need to pattern.
Pattern it.
So we're using the lithography patterning.
Yes.
Yes, yes.
Okay. So you all can listen. I may be wrong. My sirs are there to correct.
No. You can please explain. Maybe they will understand what you're trying to say.
Yeah. So for like sir not have explained in the smartwatch and the phone and all, we need those microchips, right? Chips and all. Nah. Yes or no? So they are a part of semiconductor.
Yes.
Yes. They are a part of the semiconductor. That is the main thing, right? So in order to now make the chip, we need to do something, right?
Yes.
Yes or no?
Yes.
Correct.
Yes, yes, yes.
Yeah. We need to do something. So that is called patterning, right? And we're using this lithography patterning, right?
Yes, yes. So this is a process.
Yes, it's a process. In order to make the chip, we have to use something. Okay, to make the chip now, we need to do something. So that is called this lithography patterning. So now there are 2 ways. Am I right?
Yeah, please.
There are 2 ways to make that, make the chip. Either positive resist or negative resist. We have to choose. There are 2 types to make the pattern. You understand so there?
Yes.
Yeah. So wait, now we will confused.
Now they are understanding.
Yeah.
Because the teacher
No, it's not like that.
Own teacher is teaching, yeah.
So we have two types, right? That is the positive and the negative. So here, how to say? We see, look there. There's mask. Like we have to. There are certain layers to it.
Yes, yes.
Second, there are certain layers to. I'm making it very simple. I don't know even bit. So there are certain layers to make the chip. Okay, so we have to use all those seed substrate and all those. So the mask. The mask is there, right? At the topmost.
The black one. The black one is the mask.
Yeah, so the black one is the topmost level, right? So
Yes.
so we have to use the UV rays. Yes,
Ultraviolet radiation.
Yes, the radiation, we have to use that UV rays. So now you have to help me. So when we use that UV radiation in positive resist, right, sir?
Yes.
In positive resist, when we use that radiation, right, sir? When we use that radiation,
The photoresist,
yes, the photoresist,
it becomes soluble.
it becomes soluble. Means
So you can explain what is soluble. Maybe I'm not able to explain what is soluble to them.
soluble
In
means it
your
will
own-
disappear, or it will.
Yeah. You can
right?
just, yes.
So it will disappear. Okay. When we use the UV rays now in the positive resist,
Yes.
it will disappear.
Yes.
Okay. Nothing will be there. Did you understand? Okay. And in the negative resist, it will become little hardened, like the nails like sir have explained. Very good example.
Yes.
It will become hardened and it will protect you. Did you understand?
Yes.
Yeah.
Yeah. Very
So also very hard.
excellent.
Give a big round
Look at
of
that.
applause
You
to
should be
her.
proud of such teacher with you.
Very simple, simple process.
Because you
Just try to compare this with the, let's say you want to print your t-shirt, white t-shirt.
Yes.
You want to make some design on it. What will you do? You'll take some pattern, put it on that, and then the spray color, right? So wherever the mask is, that area will be protected. Rest of the area which is open will expose to the paint, and the pattern will be done on a t-shirt, right?
Have you all
Simple.
used stencils? Stencil?
Oh, yes.
Stencil? You know what is stencil? Like the plastic, and then let us say that there is A, B, C, D.
That spatial
Which are-
scale you have, right? Where you have certain designs, for example.
So when you use a pen, I don't know how to
I
explain.
don't know. But it's,
Ah.
okay, anyway. But you understood the t-shirt while I examined, right? It's very simple.
So just think like this. Let us say this net is there, right? If I just open it. Now, understand, because there are some nets in there and there are some holes in there. So if I put sand, right? Don't you think that the sand will only go to the holes? While wherever there are nets, that will be left. So when I pick up this one, you will have a very good pattern with the sands only present where there are holes. While wherever there are nets, there will be no sand over there. Are you getting? Same thing is over here. Right, so you're just doing it through some complex process,
It's a process.
which is known as a photolithography. That's all. Understood?
Both of you are too advanced, you have too much knowledge, so you're not able to simplify it up to our level, of course. We are really down.
Or maybe because we are usually teaching to the engineering students
That's the main thing.
who already have the basic idea about all these things. So we never actually delve deeper like this.
But I think it's a good challenge for both of you.
Yeah. We are actually enjoying and we are learning that how to make you guys understand, Yeah, please.
You have given a list, not write your names.
We've already given.
Yeah.
So, sir, after this, we'll use this pattern, right? We'll use this pattern to make
At
that
every layers,
every layer.
we need to use this. Yes, layer after layer, we need to do that. So I'll show you. So can you now try to imagine that if I have different layers now, right? So we started with a silicon substrate, then we had this one, silicon dioxide, which was complete. Then we just have got this one first. Now because I need this layers over here. So what should I do? I should put this layer first. And then again I need to go for the photolithography. So that wherever I need this layers, only that should be there. From rest of the portion, I need to remove that blue layer.
So, sir, for every layer we have to do the same process.
Same process.
Yes.
Again and again.
Again and again.
Again and again. So this photolithography machines, they are extremely expensive, like very expensive. So one of the Netherlands-based company called ASML, it makes these machines for photolithography.
Chip has many layers, right? Just imagine 12-story building, right? Ground floor is all silicon. On top of that, you have oxide first floor, then
Understand.
metals, connections, right? It's a multi-story building actually. So we have to fabricate it layer by layer, right? Have you seen building which has been constructed from the top? It's not possible, right? First you have to start
We need to go from the ground on.
ground and then you.
Yes.
So that's where this happens. You have to
So-
use
So
this
all
process.
the different layers that you see in different colors, you need to follow the photolithography process at every layer. Wherever you want to keep that layer, you need to select that which particular photoresist to utilize. Hope you're understanding this now, right?
So this process is done multiple times, right? So we have mask for first layer, we have different mask for second layer, a third mask for the third layer. So every time we do the lithography and etching. So we deposit and remove unnecessary, deposit, remove unnecessary, right? And for that we use lithography and very high concentrated acids, right? Concentration level is very high, 99.99%.
So just look at this one, the final one, and compare with this one. So this is the final structure that we should have. That is your NMOS, how it looks like. Right, you can see right now, but anyways, you cannot really see when you check in the integrated circuit. Right, and I showed you that what is CMOS, which is a combination of NMOS and PMOS. Right, so NMOS is one of it, and PMOS is another process now. So
Another process.
No,
Of course.
another device, I mean.
Right.
Like
I mean, we need-
NMOS, we have PMOS, right?
because we need to use a different substrate, and also all this doping concentrations will be different for the PMOS, right? So when we have this NMOS and PMOS, when we combine it together, that is known as a complementary metal oxide semiconductor. Now that's also a process that how we can make both the things together, because this is just one. How to make both of them together if we use a single substrate? So that's a different thing. We don't want to go that much deeper, but as long as you're understanding this clearly, that is more than enough for you guys, right? So every layer which is present over here, you are getting by this photolithography process at each and every stage. Understood? Right, so you just need to understand one thing over here. The silicon dioxide layers at every stage, this layers are there which acts as an insulator. Why we need these things is because we don't really want any short circuits between the different layers. We want to protect the different layers from each other, right? Something like we put some if we don't want the sound to go outside, what should we do? We put a layer which will absorb the sound and it will not go outside, similar to that, right? So this will protect that there should not be any short circuit between any of the layers, because just think about it, that if there is any short circuit between the layers, this device is going to not work properly. It will be damaged, and if it is damaged, the complete integrated circuit can fail, and that is not right, because as I said, if the integrated circuit itself will fail, the complete device will be gone. It will no longer work. If my iPhone is having any problem in the integrated circuit, my phone will stop working, right? So even the smallest of the thing could lead to the problems, and that is why this fabrication process is done extremely carefully, and that too in a clean room. There should not be any dust particle as well which is allowed to be there. So when this deposition processes happen, let us say between these layers, if there are dust particles, it is not going to work. No, no company can afford that any normal dust particle also should be there, and that is why we need a cleaned room. There should not be anything which should be there when this device is fabricated. Clear?
Yes.
So I think that is enough. I do not want to go much more deeper than that. Otherwise, you will all beat me up. You are like, oh, sir, go away from here. Right?
Show you the TSMC process.
And I'll show you one real chip. That's how real chip looks like. I got a board for you. So that is the chip.
Oh, that has been made.
Yeah. So this is the brain. Due to this, everything will run. So you
Because
program.
of this, everything will run.
So we program this one.
Only this, no?
Yes,
This all
just this one. So these are all the peripherals. This is a switch.
From where this all comes then?
Huh?
Since we're making only this we will not make? No,
No,
Semiconductor is this.
semiconductor is this.
Okay, fine. This
Right.
one will be made by who then? All this? We don't know.
Electronics engineers.
Oh, not us, no?
But
Not the people.
you guys can do that as well. I mean, PCB, because see what happens is there is a job where how you solder these components on the board. There's also a job where you don't need engineering background. Understand?
Sir,
So-
sir, after you show us at the end, can you please tell them the scope of if you do a course on this semiconductor?
Yes.
What are the jobs that they will get?
Yes,
Okay.
yes, sure.
But, thank you.
Right? Okay. So this is LED.
So, sir, this is used where?
This is used for a lot of applications. So this is
On the phone also, no?
because we are using this in our university. So students do a lot of projects using this board.
I'll become mad if I learn all this.
No, but I think if you start working on this only, then it will be very useful for you. I mean, but then you need to continuously learn this process.
It's not English, you have to memorize it.
Yeah, you have to memorize it.
It's not for me. But I enjoy it. I like it. I learn something.
Yeah. Okay. Yeah. So this is the chip. Look at that. It's so small, right? So when we program it, it is going to. So this is switch, and this is LED. So we are going to show you one of the experiment today as well, right?
That's the semiconductor. That's the
Yeah.
The chip is the semiconductor, right?
Yes. FPGA. Yes. Semiconductor.
Since we're learning about semiconductor, that is semiconductor.
So this is the chip, right? And this is the switch. This is LED. So we programmed this chip, and because of the program of this one, we can make everything work. So if there is no chip, this is of no use. You understand? So you can look at it. This is the chip.
This is a semiconductor. So,
This one.
that's all.
So if we remove this one, this all will have no use. So we program it and we make all this thing work properly, right? So this is like a push button switch. This is also a switch, and this is a LED. So this will glow.
Connected to this one, right? Sir?
Sorry?
Everything will be connected to this.
Yes, everything is connected to this one, right? See, so this one is the chip, right? So everything is connected to this chip itself. If we remove this chip, this all thing is of no use, right? So this is like the brain, right? So yesterday you were designing that AND gate, right? So we can write the code in this one, and let us say that we use the switch and this LED. So when we turn on or off the switch, the LED can glow. So we will show you today that how to do that, right? Understand? So how small it is, right? There are so many transistors in there. These devices, what we studied, there are a lot of them inside. So this is the chip, the small one. right? And everything is connected to this chip itself. So if we remove this chip, this board is of no use. Understood? So that's the chip, right? And this chip we program, and it will be able to control the entire board. If we remove the chip, this all thing is of no use. Understood? Right? So this is like a switch. This is also a push button switch, and this is also a switch. These are the LEDs. You learned about LED, right?
Sorry?
So we are going to show you one
No.
practical today.
Sure.
Where when we
Sure.
change this,
1 to 10.
the LED
December
will
1
glow
to
on
10.
or off.
Is your festival
Right?
Okay.
And what is this device for, sir?
This is known as the
Definitely.
FPGA board.
And what's that?
FPGA board is like, this is a reprogrammable integrated circuit.
Yeah, obviously we can
While the
understand.
IC which is there in your phone, can you reprogram?
Can understand.
I don't think so.
Even
Yeah,
engineering.
exactly. And why? Because
undergrades have
what if
not
you
able to
reprogram
catch
and then it stops working? The company is not going to be accountable for that, right? So that is why
It's
they
just,
never allow you
knowledge
to
sharing
reprogram the
session.
chip which is there in your
Right.
phone or in
They
my watch.
come across the
But
new
because
things. If
this
they might
board, we use it
interested,
for
they
the
can
education
dig
purpose.
deeper into it and
This
and
should be
come up with
reprogrammable so that we can program it again and again to check that how it works.
something. Not easy.
Right.
Definitely not easy.
So this chip is known as field programmable gate
This
array.
requires very
While the IC which is in our phone, that is known as ASIC, application specific integrated
Knowledge,
circuit.
skill,
I'll write it
power,
down
yeah.
later, right?
And you have to be very get updated because this technology
So that's the chip.
growing very fast.
This FPGA
Today
chip,
is something,
right?
tomorrow will be
And this chip only when we program the chip,
Yes.
it will be
We
able to
also
run
attend such
everything.
workshop
If
where
I remove
we
the chip,
also will get
This
trained.
entire things are of no use.
Generally
at
go
all.
to industries for.
You understand?
Currently, how many students are there?
Yeah, just push button.
We have
See, you can
currently
press it.
180 students.
But when we program it, then only something will work, right?
180.
Because it is not connected yet.
And teacher?
Once you program, and these are the switch as well. So just understand that
14
yesterday
plus
you
20,
look at the AND
somewhere
gate.
around 35.
So with AND gate, let us say these are the two inputs, and LED is your output. These are the LEDs, different LEDs, and the code is dumped in here. So now it tells that these two switches will be considered as the input, and this LED will be considered as output. So now based on the truth table that you made, 0 0, which means that the switch is off, LED will remain off. When both will turn on, the LED will turn on. But that will only happen when we program it. Currently it is not
I
programmed.
mean, at
So we are going to
school
show you
level
that when we
itself
program it,
you
how
need
we can
some change,
make it
yes,
work.
Yes,
Right.
For them now, they are
So are you getting? Yeah?
because my daughter is in 5th standard. We know how to
Yeah,
make
so that's
some
the
small
FPGA,
robots.
field
and-
programmable gate array. So
No, it's
FPGA
okay.
is like a
he
reprogrammable
never, she never
integrated circuit.
studies with me.
Why we use it? Because in
For her,
education purpose, we again
our
need to
teacher is
reprogram
everything.
again and again, right? Because
If you
the
are her teacher, you
integrated circuit
say
that
that
I'm
you
using
do
in
this.
my
She will do that.
watch or on my
I'll
phone,
tell her
That is ASIC.
1,000 times.
application specific integrated circuit,
Yes.
which I cannot
You
reprogram.
no,
If I reprogram
she
my
used
watch,
to tell me
it may
you
just
are
stop
the
working.
teacher of
Who will be accountable for that?
young student.
So company
we are
cannot allow
children.
that.
I mean,
Right.
cannot.
But for
learn
education
from you
purposes, you
like
can
that.
use this reprogrammable one. So you can, whatever code you're writing, it will be dumped on this chip.
Yeah, very hot.
And based on that, this
Humid and
is going to work.
hot. But since
So maybe
last
for your
3 days they're
physiotherapy,
raining,
you must be using
so
some
it's
equipment
temperature is
which
bit
is using
down,
some
but
chips
very
like
humid.
this. You have,
Summer is
electronic-
very.
right.
Yes, like when we have to like add new programs.
So FPGA is like the most, what we can say, most reliable one. Because you do have microcontrollers as well and microprocessors as well. But compared to microcontroller and microprocessor, FPGA is like the best one. Even in satellites, right? They are sending this FPGA because it is more reliable. But then again, it's very expensive because you know that even just to get this chip, you need to go through a lot of process. That is why the things become very expensive. Right? This board only costs 22,000 or so. Just the board.
Or the whole board.
The whole board. Because what happens is that the chip will be made by this company itself, right? So Digital must have given the order to the company where they got it fabricated. Once that came back, then only they can realize this board. Otherwise, they cannot realize the board. Understood? Hello? Hello? No, you don't see? Okay. अब बताओ हम जाना पर अभिषेक
When madam comes to me,
I've experienced city life, none the village, back in the village.
अभिषेक सर को कॉल करो So we'll show you one demo on the board.
Okay. Everyone listen.
आप अच्छी बात है
Semiconductor foundry business model
आप रहो ना
with leading edge technology, unmatched manufacturing capabilities, and customer partnerships. TSMC has established a competitive advantage to unleash.
This is wafer, right?
Wafer, yes.
And this is patent wafer.
Patent.
Already chips have been fabricated. Let's see.
Chips that small chips.
Chips are already there. This whole are the chips. So what we are going to do is we are going to cut it and separate them.
हाँ सर
And you can
बताइए
see that
सर।
the modern chips are not completed. There's
पता नहीं यार अब ये लोग बोलेंगे भी लंच के लिए मुझे तो लंच के बाद हमने छोड़ देंगे
it's going to
लंच
waste.
Innovations in the
बस
global
बस हमारा भी
semiconductor
है
industry.
ना
TSMC continues to invest in
हाँ
R&D
बस तब तक हो ही
to
जाएगा हमारा
provide
भी
the
है
industry's most advanced and comprehensive manufacturing process technologies. The company manufactures a
Whole process is automated, right? With very less intervention of human. Right? Because the moment we enter, we'll unintentionally drop the dead skin or dust particle or something, right? That's why it is completely robotics. Everything is robotics.
over 10,000 different high-yield and high-quality customer-designed integrated circuits every year.
This is lithography,
Oh,
right?
lithography.
This
Process,
is
huh?
process.
You see the light right
Yes, yes, that's the
lithography process
process. Okay.
These circuits are found in smartphones, high-performance computing, IoT, automotive electronics, and consumer electronics products. Let's look inside TSMC's fab and learn about the IC manufacturing process. A TSMC fab is primarily a large clean room. To maintain the cleanliness of the production environment, entry of the fab is strictly regulated. After passing through metal detectors and undergoing ID recognition, personnel wear clean room garments, gloves, face masks, and shoes.
So this is what you have to first wear and go inside, right? So your entire body
Taiwan
will
yeah
be covered.
the Taiwan
Semiconductor
big semiconductor
After
company, like the
changing into
biggest
the appropriate attire, they enter
in the
the
world.
air wash room to remove all.
So this is air wash room, right? Very heavy airflow will be blown to, remove any dust particle from the surface.
Dust particles that could inadvertently be brought into the fab and which could impact production yield. At TSMC, the manufacturing process is closely monitored and properly protected. Raw materials, such as liquids and gases, are delivered directly to various manufacturing equipment through a maze of pipelines to
Started in 1990. 36, no, 36
so even you know
years.
Nvidia have you heard about Nvidia anybody
Nvidia graphics card.
Nvidia graphics card so that Nvidia owner is also Taiwanese and there is AMD processor as well right so that lady who is the owner she is also Taiwanese So a lot of Taiwan is into this business. Mainly for semiconductor, they are pioneers.
Without them, so it cannot work. Huh?
No.
When the world will just
The world will stop.
nothing. We will go back to the Stone Age.
We'll go to the Stone Age for sure. That will happen.
Technology.
Right? So we are coming to an end. And I'm sure that you would have learned something good. That before 3 days, where you were, and now, at least some of the knowledge you would have acquired, right? At least from the semiconductor point of view. Now, if somebody asks you, then at least you're in a state to answer, yes or no?